Hi, I'm Wilbur, and this is my LLM arithmetic coder, which I am very excited to show off to you all. So, first, I'm going to explain what an arithmetic coder is, then explain how I use LLMs to produce the underlying probabilistic distributions that fuel this algorithm. But first, what is this? So, this is a compression algorithm, so we can take an input text like the Declaration of Independence, and condense it into a smaller string. And this arithmetic coder condenses it into a singular decimal number between 0 and 1. And in this site, I use a base 64 representation of that number. Then we can take that number and decompress it to get our original string back completely lossless. And this version of the arithmetic coder using LLMs is actually a significantly more effective compressor, meaning it produces an encoded output in less bytes than compressors on your computer like gzip, bzip, and xz. So how does arithmetic coding work? Let's say you have an alphabet of A, I, and X. So these are the only possible characters that a user can input. And the user types in A, I, X, I. All we need to encode this is these 4 PMFs. And then the process is we go one character at a time, and I'm going to say tokens from now on, and we plot these PMFs, the probabilistic distributions, onto a number line from 0 to 1. And each segment represents each possible token that can be inputted. So we look at our first token, A, and we see where it is on the number line, and we know that our encoded output is going to be between 0 and 0.45. Then we treat this segment as a new number line from 0 to 1 and split it up using the conditional probabilities of each possible token, given that we have A times the probability that our first token was A. So we have this new number line, and we look at our second token, and where does it map on the number line? It means that our encoded output is going to be between 0.09 and 0.36. Then we split up this section into a new number line, and we continue doing that for every token until we get the full picture here, where we have our complete input mapped to a segment from 0 to 1, and in this case, AIXI is mapped to 0.322 to 0.341. And in the code, we use binary, so this string in binary is a number between, in this segment, 0.328125, and that maps back to our input, AIXI. So when we decode this, all we have is this number, and we can go back to our original number line, splitting it up, using our PMFs again, and we look, where's our number, 0.32 whatever. It's in this segment. We know our first token is going to be A. Then we split it up using the conditional probabilities again, and we look, where's our number, 0.32 whatever. It's here, so we know our second token is going to be I, and we keep doing that until we get our original token AIXI. So how are we able to use LLMs here? What we would need to do an actual compression algorithm is we would need PMFs for every possible token given any other possible combination of tokens. And LLMs are the perfect tool that we can use to produce these PMFs. So imagine we have our alphabet is every possible token in language, and then we can create PMFs for each of those tokens and map it on the number line and do this same process using every possible token and calculate these conditional probabilities using the LLM's PMFs. And why does this work so well? Well, it's not a coincidence. LLMs and compression share the same objective. So when these big companies train their models, what they're trying to do is get the distributions behind their models as close as possible to the true distribution of language. And what that means is they're trying to reduce the entropy of their distributions as much as possible. And that, according to Claude Shannon, the best possible compression algorithm is equal to the entropy of the true distribution. So when they're improving these models, when they're training these models, when they get closer to the true distribution, it means that my LLM arithmetic coder gets closer to the perfect compression algorithm. And if you want to learn more about that, check out my write-up and check out a paper called Language Modeling is Compression, which came up with this whole idea. And that's it. Thank you.